Another interesting cycle is the Stirling cycle. It's another completely reversible cycle and so has the same efficiency as the Carnot cycle. It was invented and engines based on it built by Reverend Dr. Robert Stirling during his lifetime. And he was both a pastor and an engineer. He was Scottish. His grandfather had invented a threshing machine. Some of his brothers, as I recall, became engineers, his sons as well. And so it obviously ran in their blood, as well as, I guess, ministry, because some of the family were also in ministry. But in looking at this idealized Stirling cycle, let's start at the beginning at state 1. There's actually 2 pistons that are involved in this machine, or this cycle. And the really interesting part of this is something called the regenerator. Stirling called it the economizer. Basically, the types of engines he was building was called, well, they still are called, hot air engines. And these engines, rather than using steam as their working fluid, use air as their working fluid. But whereas there were steam boilers at his times and lots of explosions and people being killed, and that's apparently one of the reasons for inventing this engine. The next cycle we'll study is the Stirling cycle. It was invented by Reverend Dr. Robert Stirling. He built several engines based on it, and the key difference in this engine, the key idea and useful advancement is the regenerator. He called it the economizer. Now, at the time he was alive, the Industrial Revolution had taken off and there were lots of steam engines around that involved boilers, and of course there were a lot of boiler explosions as well that happened and tragically killed a lot of people. Not sure if that's the reason he invented this or not, but it is different in the sense that instead of having steam come in at high pressure and heat it up and then toss it out from a locomotive, for example, or even operate in a closed cycle, this engine used air that stayed inside of the engine, so the engine didn't cycle through it. So it was an external combustion engine like the typical steam engine, but it used air as the working fluid without passing the working fluid in and out. So it used this economizer, and you'll see how that works here in just a second. It's a really interesting cycle and gives rise to some improvements for other cycles. There are Stirling engines that have been developed. There's one in particular in a video I'll have you watch where a submarine actually uses the Stirling cycle, and to very interesting effect. There are Stirling engines that have been developed for use in space and other applications. You'll see some in the next slide. But anyway, state 1, let's start with it. We've got 2 pistons involved here. And the way this thing works is you transfer thermal energy via heat into the air. You see Qn coming in at TH. Now, the piston on the left is allowed to expand doing work during this process. And so we're moving from state 1 to state 2. In the TS diagram at the top, you'll notice that this is heat being added at constant temperature. So the entropy of the air is increasing, but the temperature remains constant. Of course, the volume's increasing as well during this process. So then, finally, we're at state 2 where the piston is fully expanded, and now we actually allow the piston, the 2 pistons, to move together at constant volume. Now, unfortunately, there's an arrow pointed to the left. I should probably remove that in this diagram. It's the second one down. At this point, the piston is finished moving to the left, and actually both pistons move together to the right. Now, that colored object in between, the sort of rainbow colored or gradient colored object, is an economizer or regenerator, and it's basically a porous material that can absorb thermal energy. So as the air is pushed to the other side, you see as we move from state 2 to state 3 at constant volume, the air is pushed through this porous plug, if you will. And what happens is the porous plug has a temperature gradient across it. It's hot on the left side, that's what's indicated by the red color, and then on the right side where it's blue, it's cold or relatively cool. And as the air is pushed through that regenerator, it deposits thermal energy into the regenerator. Pardon me. So the gases go from TH down to TL and lose energy, but not because they're not by a heat interaction or a work interaction. What's so unique about this is that they lose heat by regeneration. They set it aside temporarily. That way it's not thrown away. This is a very clever thing. And so you look in the TS diagram, you'll notice that from state 2 to state 3, there's a gray arrow that says regeneration. And the idea there is that this is a heat flow, or heat being set aside, or thermal energy, I should say, being set aside for later use. So if the gas, now understand that this is all very idealized. We're assuming that this porous plug is perfect in the sense that there's no pressure loss as the air goes through it. All that happens is the temperature drops, and there's no flow resistance in it. Obviously, that's a very highly idealized thing. If you have a true regenerator, there's going to be some loss in it. But this is the ideal Stirling cycle, so let's continue. So the gases come out of the regenerator on the right side at a lower temperature TL, and now we're at state 3. Now at this point, again, I don't like the arrow to the right on state 3. That's actually not, the piston does not continue moving to the right, rather it moves to the left. And in this process, ideally the piston on the left stays still as the piston on the right goes from state 3 to state 4, moving to the left. And what happens during this process as the piston on the right moves inward is the waste heat is rejected to the atmosphere or the local environment or whatever the heat sink is, so that the temperature remains at TL. So that's the process from state 3 to state 4. And then what's not shown here is that the two pistons again move together to the left to come back up to state 1. Now understand that when the pistons both together move to the left, the volume of the system is constant. The volume of the air is constant, but the air now has to move back through the regenerator and pick up the heat that it left behind, or the thermal energy that it left behind before. So this is where the regeneration is completed, and the air picks up the energy that it set aside earlier. So you can see all of this on the TS diagram, where that last process is a constant volume process. So isothermal expansion with heat addition is from 1 to 2. Constant volume regeneration, or in other words storage of the energy, is 2 to 3. Isothermal compression with heat rejection then is 3 to 4. And then finally, coming back to the beginning, is constant volume regeneration, or retrieval of the energy that was set aside in the economizer or the regenerator. The Stirling engine actually was used before electricity became common. It was fairly easy to build a relatively small engine, but more challenging to build larger engines. Since the flame was external, or the heat source was external to the engine, you had to somehow get it in, and whatever material, typically a steel, that the heat flowed through, well, it really damaged that material over time. And so the Achilles heel of the Stirling engine, it was is the whatever surface the heat has to flow through to drive the engine. But it was still in common use for pumping water on farms, or for running a fan with a flame. It was an external combustion engine, so all you needed was a flame, and you impinged the flame on a certain area of the engine, and the engine would start moving. So it was a very useful engine, and there's several advertisements. If you download the slides and have a look at them, there's articles on this. There's several different pictures of advertisements on the next slide that I've hidden. I just have never had a chance to organize it. It's just drag the pictures around and you can see all the different. Most commonly, these things were used for pumping water, or the lake breeze fans were very popular, common. If you ever get your hands on one, it's probably an antique and worth hanging on to. There was another completely reversible cycle called the Ericsson Cycle. Instead of using piston cylinder devices, this one uses a compressor and a turbine, but it also involves regeneration. So let's follow this through. From state 1 to state 2, for example, is expansion with heat addition. Where's that? Well, that's in the turbine. So look at the turbine on the right. And what's happening is state 1 is the state of the air coming into the turbine. State 2 is the state of the air leaving the turbine. Now, heat is added to the air as it expands in the turbine. Remember that to get more work out of a working fluid, you really want that working fluid to have as high specific volume as possible. So adding heat at this stage tries to continue to increase the specific volume of the air as it flows through. Now, that's 1 to 2 is isothermal expansion with heat addition. And in the ideal cycle, you manage to hold the temperature of the air constant even as it expands. So if you look at the TS diagram, you'll notice the TS diagram looks exactly like the Stirling cycle, except for the constant pressure, heat addition, and rejection. But we'll get to that in just a second. So, I'm sorry, the constant pressure, regeneration, and retrieval. I'm sorry, I messed that up. So the constant temperature heating occurs in the turbine, and then we're at state 2, which is after the turbine. From state 2 to state 3 is the first pass through the regenerator. That's where there's constant pressure, and so the idea is that this is just a heat exchanger, and then basically the heat exchanger is just a couple of open pipes that can transfer heat to each other. And so the idea is that there's no loss. In the real world, obviously, there is some pressure loss in the regenerator, but for our purposes, we're going to use the ideal Ericsson cycle, so we're going to neglect any of the losses in the regenerator and move from state 2 to state 3. So here's our constant pressure regeneration or storage, where heat is not lost to the cycle, but it's set aside because there's still a significant amount of thermal energy in the air as it comes out of the turbine. So then the air goes into the compressor from state 3 to state 4 and ideally loses heat at constant temperature. So in other words, as the air is compressed, if you just take air and you compress it, it will naturally warm up. And so if as you compress it, you cool it down and you've got everything set up just right, you could maintain the air temperature constant. Now again, this is a very idealized thing, but that's the concept here. And then from state 4 to state 1 is the exit of the compressor to the entrance of the turbine. And what's happening there is retrieval. Remember that energy that was set aside, well actually that at the present time is being set aside by other air flowing through the regenerator, is being picked up then by the flow from the compressor to the turbine. So this again is constant pressure regeneration because it's in a heat exchanger where the pipe is just open. So from state 4 to state 1 is constant pressure regeneration. And you can see the associated PV diagram there as well. Now these engines aren't necessarily all that practical. There are significant problems with them, but it does give an idea to improving the gas power cycle we saw before called the Brayton cycle, or the gas turbine engine. If you'll notice, this is a figure, or this figure is a picture of the gas turbine engine, right? Instead of trying to accomplish compression at constant temperature or expansion in the turbine at constant temperature, rather than doing all of that, the most important and most useful pieces of the Stirling cycle and the Ericsson cycle, the regenerator, is being incorporated here. And it's pretty simple because it's just a heat exchanger. So as the compressor brings in air and compresses it to state 2, you might realize, well, wait a second, why are we spending so much money in the regular cycle to burn fuel, heat up this air to go into the turbine, when the exhaust gases coming out of the turbine are still very warm by comparison to the compressed air coming out at state 2, out of the compressor? Well, you don't have to, right? You could take the exhaust gases, which are really hot coming out of the turbine, and preheat the air that is leaving the compressor. That way, you don't have to pay for as much fuel in the combustion chamber to heat up the air from state 5 to state 3 as you would have to go from state 2 to state 3. You get to reuse some waste energy. And this is a good idea because as long as the temperature of the waste energy is still high enough, that energy still has quality and can be used to regenerate or improve the efficiency of this cycle. So this is a very clever idea based on Stirling and Ericsson's regenerators or economizers. Now the maximum temperature that we can bring stream 5 to is the temperature of stream 4. Stream 4 is the exit of the turbine, and although stream 3 is at a higher temperature, it wouldn't make any sense to use stream 3 to heat stream 2 because whatever's at stream 2 is going to come, or state 2, is going to come into the combustion chamber. So although state 3 is the highest temperature, state 4 is the maximum temperature that we could hope to bring state 5 up to. You see, the air that's coming into the regenerator out of the turbine can only transfer heat until the temperature has been equilibrated, right? Until thermal equilibrium is reached with state 5. So there is a limit to how much heat can be regenerated, but it's better than throwing it away. So if we look at the ideal Brayton cycle with regeneration, here's the TS diagram for a gas turbine cycle, but it's been modified to include regeneration. You'll notice that the state numbers have remained constant at 1, 2, 3, and 4, just as in the regular gas turbine. There are a few states that have been added, though, state 5 and state 6. Now, the reason for these, of course, is that now we have another piece of equipment, the regenerator or the heat exchanger, and that piece of equipment changes the state of the air, of course, right? So from state 1 to state 2, let's follow the TS diagram. There is compression. It's not isothermal compression. The temperature does increase. And then from state 2 to state 5, and instead of going from state 2 all the way up to state 3 by burning fuel, from state 2 to state 5, what happens is heat is brought in from the regenerator to preheat, if you will, the air before it goes into the combustion chamber. And then the heat load, Qn, only has to raise the air from state 5 to state 3. So this is an improvement. From state 3 to state 4 is expansion in the turbine, and then from state 4 to state 1 would normally be the loss, right? Normally you would just take this air in the gas turbine cycle, throw it out in the atmosphere, and you're done with it. But in the Brayton cycle with regeneration, instead what happens is from state 4 to state 6, the hot gases are moving through the regenerator and giving up energy to the incoming air that's coming out of the compressor going into the combustion chamber. So it's preheating the air in the before the combustion chamber. So you see that regeneration line as we had with the Ericsson and the Stirling cycle. And so the drop from state 4 to state 6, all of that heat is saved, right? It's reused instead of just being thrown away. And then from state 6 to state 1 is the amount of heat that's actually thrown away out of the engine. So this is a significant improvement. In fact, Stirling's engines were used partially because they were so efficient. They were significant improvements on what was available at the time. So the actual regeneration amount that we can get is the difference between the enthalpy at state 5 and state 2, right? That's proportional to the rate of heat transfer that's saved. So Q regen, the amount of heat saved, is just the difference between the streams at state 5 and state 2. Because that's the heat that's flowing in from the combustion chamber, from the regenerator, the heat exchanger. So what's the maximum amount? How much heat can be saved at maximum? Well, to figure that out, we have to understand that the highest temperature that we have access to for use in regeneration is the temperature at stream 4. Therefore, what that means is that the maximum temperature at stream 5 would be T4, right? Because if this regenerator or heat exchanger did the best it could, the highest temperature it could achieve on the cold side, which is state 2 to state 5, the highest temperature it could achieve would be the temperature at state 4. And so what that means is that the highest enthalpy that stream 5 can achieve is the enthalpy of stream 4, because think about it. If we're talking about air as the working fluid, air is an ideal gas, right? At least for the temperatures and pressures we'd be working with here. And so the enthalpy and temperature just go hand in hand. And so the maximum enthalpy we could expect in stream 5 would be equivalent to the enthalpy in stream 4. So the maximum amount of heat transfer we could expect is the enthalpy in stream 5 minus 2, which, again, H5 max is H4. Okay, and the key here to understanding this is realizing that the highest temperature we can bring stream 5 to is the temperature of stream 4. So we can finally define an effectiveness of an actual heat exchanger as the amount of heat that's actually regenerated divided by the maximum amount of heat regenerated. And if you remember 220, this is how we defined it for heat exchangers in 220 before. So the actual heat regenerated is H5 minus H2. The ideal would be H4 minus H2. That ratio can be approximated as the temperature difference T5 minus T2 over T4 minus T2. So there's our regenerated effectiveness. Now, if you don't understand all of this to this point, that's okay. I would like for you to. What you really need to know is that equation in the box. That's what we're going to use whenever we have the Brayton cycle with regeneration. Here's some lessons learned. If you go through and you analyze the thermal efficiency of the Brayton cycle with regeneration, it's a little bit more complicated, so I've spared you the details, but here's the results. The thermal efficiency of the Brayton cycle with regeneration is 1 minus T1 over T3 times the pressure ratio to an exponent dependent on the heat capacity ratio of the working fluid, most commonly air. Now, T1 and T3, where are those again? Let's go back and look at them. T1, that's the incoming temperature coming into the compressor. T3, that's the incoming temperature into the turbine. Why those two temperatures? Well, realize that those are the low and high temperatures respectively. So T1 is the lowest temperature in the entire cycle. T3 is the absolute highest temperature in the cycle. So it shouldn't be a surprise that these temperatures are important. As a matter of fact, this looks a lot like 1 minus TL over TH, doesn't it? The only thing is we've got this pressure ratio then to the power of K minus 1 over K. And so what you see from this is that the pressure, let me back up, as the pressure ratio increases, you actually end up with a decrease in efficiency. Now that's a wonderful thing for us if you think about it, because the regular gas turbine, we needed high pressure ratios to get efficiency out of the thing. And that's a problem if you're trying to put this engine into a helicopter, because high pressure ratios means a lot of metal so the engine doesn't blow itself apart. And we'd like to avoid a lot of metal, right? We'd like to have light engines. Well, this gives us an opportunity to build a light engine that is very efficient. Now understand that this is not more efficient than the Carnot cycle, for example, because the pressure ratio has to be greater than 1, and then with the exponent, the way it's set up, you always end up with a multiplier greater than 1. And so you're subtracting more than would be ideal from 100% efficiency. In other words, the 1 minus, we'd like to minimize what comes after the minus sign, right? And Rp to the K minus 1 over K only increases the temperature ratio, T1 over T3. But we found something wonderful, because with regeneration, the higher efficiency is actually on the lower end of the pressure ratio side. So that means we can have fairly efficient light engines because of the regenerator. So the only cost really is a heat exchanger, which is a fairly well-known, simple-to-use device, and we can have good engines that are efficient. Now you'll notice that the temperature ratio also makes a difference, and the larger, let's see, make sure I get this right. Yeah, the larger the temperature difference, the higher up we are on those curves, right? So as T1 decreases or T3 increases, you get a smaller ratio, and so that gives you a higher efficiency.